Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals x cubed plus 3x squared minus 7x plus 2. The first thing to do is find the domain. F of x equals x cubed plus 3x squared minus 7x plus 2, which is a polynomial, and a polynomial has a domain that is all real numbers, or negative infinity to positive infinity. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F prime of x equals, the first term is power rho, bring down the power, subtract 1 from it. Second term is power rho, bring down the power, multiply it to 3, subtract 1 from it. Third term is a constant times x, derivative is the constant. Fourth term is a constant with no x, derivative is a 0. We can now find the second derivative. First term is power rho, bring down the power, multiply it to 3, subtract 1 from it. Second term is a constant times x, derivative is the constant. Third term is a constant with no x, derivative is a 0. We want to fully factor the second derivative. There's a common factor of 6. Factoring that out, we'll leave behind x plus 1. We can now set the numerator equal to 0, and the denominator, if there is one, also equal to 0, and solve for all x's. The x plus 1 factor will give us x equals negative 1. We now will check to see if this is in the domain. The domain is all real numbers. X equals negative 1 is a real number. It's in the domain, and it is therefore a candidate number, and is a candidate to be a possible inflection point. We can now draw a domain line, a line representing the domain. It has no left end because it starts at negative infinity. It has no right end because it ends at positive infinity. We can put all candidate numbers on here. We have x equals negative 1. That breaks the domain interval up into two separate intervals. We can pick a test value in each of the intervals. We have the negative infinity to negative 1 interval. Negative 10 is in that interval. And we have the negative 1 to positive infinity interval. 0 is in that interval. We can now test the concavity in each of these intervals by plugging the test values into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. The best place to plug in is the fully factored version, which is this one. Starting with negative 10 plus 1 is negative times a positive 6 is still negative. We have a negative second derivative. This corresponds to concave down. We can now plug in the test value of 0 into the fully factored version of the second derivative. 0 plus 1 is positive, times a positive 6 is still positive. We have a positive second derivative. This corresponds to concave up. So we have a concave down interval from negative infinity up to negative 1. We have a concave up interval from negative 1 to positive infinity. Right at the candidate number of x equals negative 1, we have the concavity changing from concave down to concave up. That makes x equals negative 1 be an inflection point. So we have an inflection point and an x-coordinate of negative 1 and a corresponding y-coordinate that can be found by plugging the negative 1 into the original function. So y equals f of negative 1, which will be negative 1 cubed plus 3 times negative 1 squared minus 7 times negative 1 plus 2. Negative 1 cubed, because of the odd power, is a negative, and 1 cubed is 1, plus 3 times negative 1 squared, because of the even power, is positive. 1 squared is 1. And minus 7 times a negative 1 is a positive 7, plus 2. So we have a negative 1, plus 3 times 1 is a 3, 7 plus 2 is a 9, Negative 1 plus 3 is a 2, plus a 9 is an 11. So this has a corresponding y-coordinate of 11. So we have one interval of concave down, one interval of concave up, and we have an inflection point at negative 1, 11.